Recent black hole discoveries are changing what scientists thought they knew about the darkest objects in the universe. Some appear too massive, too early, and too powerful for simple explanations. They bend light, disturb galaxies, and hide regions where even time behaves differently. In this video, the journey moves from the farthest galaxies to the edge of the event horizon, where light itself struggles to escape. Watch until the end, and before the journey begins, please like this video, subscribe to the channel, and stay with the story of the universe's most silent darkness. Across the widest reaches of the universe, space appears calm and dark, yet it carries subtle signs of powerful structures that do not emit light. Among these structures are black holes, objects defined not by what can be seen directly, but by how they shape their surroundings. At the largest scales, the universe presents itself as a vast network of galaxies arranged along faint filaments, with enormous regions between them where matter is sparse. Within this quiet structure, black holes are not isolated curiosities, but persistent features, woven into the evolution of cosmic space. In this distant view, black holes do not appear as solid forms. They reveal themselves through motion and energy. Gas clouds drift and stretch in unusual ways. Stars accelerate along curved paths, and light from faraway sources bends slightly as it passes through regions of strong gravity. These effects are gentle at first glance, requiring careful observation over long periods. Telescopes gather faint signals, and instruments measure shifts in position and brightness, allowing scientists to infer the presence of objects that cannot be directly imaged. Observations indicate that many galaxies host black holes at their centers, often with masses that reach millions or billions of times that of the Sun. These central black holes remain invisible unless they interact with nearby matter. When they are quiet, they blend into the background, detectable only through the motion of stars orbiting at great distances. When they are active, they become sources of intense energy, not from the black hole itself, but from material falling toward it. This activity can outshine the entire galaxy for a time, creating what is known as a quasar, a luminous region powered by accretion, the process of matter gathering and spiraling inward under gravity. At these outer cosmic distances, black holes appear as distant influences embedded within larger systems. Their presence is inferred through patterns that repeat across the sky. In some regions, clusters of galaxies show coordinated motion that cannot be explained by visible matter alone. Gravity extends beyond what can be seen, and within that hidden mass, black holes contribute alongside other forms of matter. The precise distribution remains uncertain, as observations provide indirect evidence rather than direct measurement. It is known that black holes occupy a range of sizes, from stellar remnants to supermassive forms, yet their total contribution to cosmic structure continues to be studied. Light traveling across billions of years carries information about these distant regions. As it moves through space, it passes near massive objects, including galaxies and clusters that may contain black holes. Gravity bends the path of this light in a process known as gravitational lensing, where the apparent position of a background object shifts, and its image may stretch or multiply. Through careful analysis of these distortions, astronomers map the mass of intervening structures. In some cases, the patterns suggest compact concentrations of mass that align with the expected properties of black holes. The universe at this scale unfolds slowly. Changes occur over spans far longer than a human lifetime. Black holes grow by absorbing matter and merging with one another, but these processes take place over millions to billions of years. observations capture only brief moments within these long sequences. By comparing distant objects at different stages of development, scientists reconstruct a timeline, placing black holes within the broader evolution of cosmic history. The picture that emerges shows that black holes are not rare anomalies but common outcomes of the universe's structure. Despite their abundance, uncertainty remains about how some black holes reach enormous sizes so early in cosmic history. Observations of very distant quasars suggest that supermassive black holes already existed when the universe was young. The mechanisms that allow such rapid growth are still under study. It is known that gas accretion and mergers contribute, yet the exact balance between these processes is not fully established. Measurements continue to refine estimates of mass and age, narrowing the range of possible explanations without settling on a single path. In this outermost region of observation, distance softens detail. Individual events blur into patterns, and the focus shifts from specific objects to the overall behavior of the universe. Black holes act as anchors within this structure, shaping the motion of matter and influencing the flow of energy. Their effects extend far beyond their immediate surroundings, guiding the formation of galaxies and affecting the distribution of gas over vast scales. The quiet darkness between galaxies holds no visible sign of these objects, yet their influence reaches across it. Gravity does not diminish suddenly but fades gradually, allowing black holes to affect regions far beyond what can be seen directly. This influence remains subtle, detectable only through precise measurement and long observation. The universe, in this sense, carries a hidden framework, where unseen objects play a central role in shaping visible patterns. As the gaze remains fixed on this distant field, the understanding of black holes begins not with their interiors, but with their imprint on the cosmos. The outermost perspective provides context, showing that these objects are part of a larger system rather than isolated extremes. Their presence is established through consistent, measurable effects that repeat across space and time. This foundation allows a gradual movement inward, from the broad cosmic background toward regions where black holes become more distinct, though still defined by their influence rather than direct appearance. In the early universe, the light now reaching modern telescopes has crossed an immense distance and an immense span of time. It begins its journey when galaxies are still young, when the first large structures are still gathering from gas, dust, and dark matter. In this region of the subject, black holes appear not as nearby objects with sharp details, but as ancient signals. Their presence is carried by faint radiation stretched by cosmic expansion, so that light once emitted at higher energy arrives softened and shifted toward longer wavelengths. This stretching is known as redshift, a measure of how much the universe has expanded while the light has travelled. Observations of very distant galaxies show that black holes are already present surprisingly early in cosmic history. Some of them are active, meaning that matter is falling toward them and heating as it gathers in a compact region around the center. The light from such activity can make a young galaxy visible across vast distances. In these cases, the black hole itself remains unseen, but the heated matter near it acts as a beacon. It allows astronomers to study a time when the universe is much younger than it is now. The difficulty is not only distance. Early black holes are surrounded by young galaxies that may be small, dusty, uneven, and still forming stars rapidly. Their light mixes with the glow of newborn stars, hot gas, and heavy elements beginning to spread through space. Separating the contribution of the black hole from the surrounding galaxy requires careful measurement across many wavelengths. Infrared telescopes are especially important because much of the early light has been stretched into infrared by the expansion of space. X-ray observations also matter because active black holes can produce high-energy radiation from hot inner gas. The new discoveries that unsettle older expectations come from the apparent maturity of some black holes at very early times. Several distant sources suggest that massive black holes may have grown quickly, perhaps faster than simple models once allowed. These observations do not mean that known physics has failed, but they do require closer attention to the first stages of black hole formation. Scientists consider different paths. Some early black holes may begin as remnants of the first massive stars. Others may form from the direct collapse of large gas clouds under special conditions. Another possibility is that repeated mergers and steady feeding allow smaller seeds to grow rapidly. It remains uncertain which path dominates. The word seed is used for an early black hole that later grows into a much larger one. A light seed begins with a mass closer to that of a collapsed massive star. A heavy seed begins much larger, perhaps from a dense gas cloud that falls inward without first making many stars. Both ideas remain under investigation. Observations indicate that at least some early black holes become large within a short cosmic interval. The question is how often this happens and under what conditions. The answer depends on the supply of gas, the rate of growth, the effect of radiation pushing material away, and the mergers of young galaxies. In the wide early universe, matter does not yet sit in the settled patterns seen in mature galaxies. Gas streams along dark matter filaments and gathers in shallow wells of gravity. Small galaxies collide and combine. Star formation rises in bursts. In such environments, a growing black hole may receive gas from many directions. The gas can lose energy through radiation and sink toward the center, forming a compact feeding region. Yet the same process also releases energy. Radiation, winds, and jets from active black holes can heat or expel nearby gas, limiting further growth. Growth therefore depends on a balance between feeding and feedback, where feedback means energy returned to the surroundings. Some early black holes may be hidden by dust and gas. If a young galaxy contains dense material around its center, visible light from the active black hole can be absorbed and re-emitted at longer wavelengths. This makes the object harder to identify with ordinary optical surveys. Infrared and X-ray measurements help uncover these obscured sources, but even then the evidence can be incomplete. A faint source may be a small active black hole, a compact burst of star formation, or a mixture of both. Careful modeling is needed and uncertainty remains when the signal is weak. The discoveries are significant because they connect black holes to the first large changes in the universe. As young galaxies form, their central black holes may influence how gas cools, how stars appear, and how heavy elements spread. Heavy elements are made in stars and stellar explosions, then carried into surrounding gas. In active galaxies, outflows from near the central black hole can move enriched material outward. This process can alter the later growth of the galaxy. At early times, even a modest change in gas flow may have lasting effects, because the system is still small and unsettled. The oldest observed active black holes also help mark the timing of cosmic transformation. After the first atoms form, the universe enters a long dim period before the first stars and galaxies light the surrounding gas. Later, radiation from early stars, galaxies, and active black holes helps ionize much of the hydrogen between galaxies. Ionization means that electrons are separated from atoms. The exact role of black holes in this transformation remains uncertain. Stars are likely major contributors, but active black holes may add high-energy radiation in some regions. Their influence depends on how common they are how bright they become, and how much radiation escapes their host galaxies. From this early outer layer of black hole discovery, the main picture is one of growth beginning sooner than expected in some places. The universe is young, but already complex. Galaxies gather, gas falls, stars ignite, and black holes appear within the same forming structures. The evidence does not show black holes as sudden monsters outside nature. It shows them as difficult, compact outcomes of gravity working in dense environments. Their early presence is serious because it compresses the available time for formation and growth. It asks for a clearer account of how matter collects so efficiently, how radiation fails or succeeds in slowing the process, and how the first dark centers become part of the bright young universe. At the scale of galaxy clusters, black holes are studied through a wider gravitational setting. A galaxy cluster is a large gathering of galaxies held together by gravity, along with hot gas and dark matter spread through the space between them. It is one of the most massive structures in the universe. From the outside, a cluster may appear as a field of separate galaxies, but its full structure is much larger than the visible points of light. The galaxies move within a shared gravitational well, while hot gas fills the spaces between them and emits X-rays. Hidden within many of those galaxies are central black holes, and the combined mass of the cluster bends the path of light from objects lying far behind it. This bending is called gravitational lensing. It occurs because mass curves space-time, and light follows that curved path in a cluster. The effect can become strong enough to stretch the image of a distant galaxy into a long arc, duplicate it into several images, or magnify light that would otherwise be too faint to detect. The lens is not a glass object. It is the gravity of the cluster itself. The distorted light provides a map of the mass inside the cluster, including mass that does not shine. Through this method, astronomers study distant galaxies and sometimes the active black holes inside them, using the cluster as a natural telescope. The outer cluster environment is broad and layered. Galaxies drift through it at high speeds, while thin, extremely hot gas spreads between them. This gas is known as the intracluster medium, meaning the matter between cluster galaxies. It can reach temperatures of millions of degrees Celsius, so it glows in X-rays rather than visible light. At the center of many clusters lies a very large galaxy, often containing a supermassive black hole. When gas slowly settles toward the center, some of it may feed this black hole. The surrounding region can become active, releasing energy that changes the temperature and motion of the nearby gas. In the cluster setting, a black hole's influence is not measured only by what disappears into it. It is also measured by what it prevents. Hot cluster gas should cool over time, and if it cools efficiently, it should fall inward and form large numbers of new stars. Observations show that this expected cooling is often reduced. One explanation supported by many studies is feedback from the central black hole. Feedback means energy returned to the environment. Jets and outflows from the active center inflate large cavities in the hot gas, like bubbles carved into a glowing atmosphere. These cavities do not require the black hole to be seen directly. They appear in X-ray maps as regions where less hot gas is present. The energy involved is immense, yet the process can unfold steadily. A central black hole may enter an active phase when gas reaches its surroundings. The falling material forms a hot, rotating structure and releases radiation, winds, or jets. These jets push into the intracluster gas, lifting and stirring it. The heated gas then resists rapid cooling. In this way, a compact object near the center influences a region far larger than itself. The connection between small-scale and large-scale is one of the key discoveries of modern cluster astronomy. A black hole only a tiny part of the cluster's size can help regulate the thermal state of gas spread across hundreds of thousands of light years. Gravitational lensing adds another layer to this view. The cluster's mass magnifies background galaxies, and some of those distant galaxies host growing black holes. Because the light is magnified, telescopes can detect objects that would otherwise remain below the limits of observation. This makes galaxy clusters useful for studying faint black hole activity in the distant universe. The lensing pattern must be modelled carefully. The mass of the cluster, the positions of member galaxies, and the distribution of dark matter all affect the final image. When several images of the same background source appear, their positions and brightness help refine the model. Not every compact source revealed by lensing is clearly a black hole. A bright point in a distant galaxy may come from active accretion, intense star formation, or a combination of both. X-ray emission, infrared color, spectral lines, and changes in brightness help separate these possibilities. Spectral lines are narrow features in light that show the presence and motion of particular elements. When the lines are broad or shifted in certain ways, they may indicate gas moving rapidly near a black hole. Still, uncertainty remains for faint sources, especially when the object is extremely distant or partly obscured by dust. Clusters also provide evidence for wandering or displaced black holes. During galaxy mergers within clusters, central black holes may be pulled away from the exact center of their host galaxies, or pairs of massive black holes may form as two galaxies combine. Detecting such cases is difficult. Astronomers look for unusual motion, offset active cores, disturbed galaxy shapes, and compact X-ray or radio sources away from the usual center. Some candidates exist, but each requires careful testing because other processes can imitate the signal. The cluster environment is crowded and dynamic, so interpretation must remain cautious. The most massive clusters act as laboratories where gravity, gas physics, galaxy evolution, and black hole activity meet. Their lensing maps show where mass lies. Their X-ray glow shows how hot gas behaves. Their radio emission can trace jets and lobes produced by central activity. Their galaxies carry evidence of past mergers and long-term growth. Together, these observations reveal that black holes are not only endpoints of collapse, but also participants in a larger cosmic balance. They feed from their surroundings, and their surroundings respond. From this region of the topic, the discoveries are not terrifying because of immediate danger. They are unsettling in a quieter scientific sense because they show how far the reach of a black hole can extend through ordinary cosmic matter. The strongest influence is not always a sudden, devouring event. It can be a long regulation of gas, heat, and structure across a galaxy cluster. In the bent images of background galaxies and the hollow cavities of hot gas, black holes appear indirectly but clearly. They are small compared with the cluster, yet their effects become written across the largest bound structures in the universe, leaving calm but unmistakable signs in light that has travelled for billions of years. Across the distant universe, some of the brightest known objects are powered by black holes hidden inside young galaxies. These objects are called quasars, a name used for extremely luminous active galactic nuclei. An active galactic nucleus is the bright central region of a galaxy, where gas falls toward a supermassive black hole and releases energy before crossing the point of no return. At great distances, the surrounding galaxy may be faint or difficult to separate from the central glow, so the quasar appears almost like a single bright point. Its light has travelled for billions of years, carrying information from a time when galaxies are still assembling and central black holes are already growing. A quasar does not shine because the black hole emits light from within itself. The light comes from matter outside the black hole. gas loses energy, gathers into a rotating flow, and heats as friction, compression, and magnetic activity transform gravitational energy into radiation. The black hole provides the deep gravitational well, while the surrounding material provides the glow. At distant cosmic times, this glow can be so intense that it outshines all the stars in the host galaxy. The central source may therefore dominate the telescope image, masking the softer structure around it. The most distant quasars are important because they show that some supermassive black holes reach enormous masses early. Their brightness can be used to estimate the rate at which gas falls inward, while the motion of gas near the center can help estimate the black hole's mass. These estimates are not simple direct measurements. They depend on models of the emitting gas, the angle of the system, the strength of radiation, and the way spectral lines broaden. A spectral line is a feature in light linked to a particular atom or ion. When gas moves rapidly near a black hole, these lines can widen, showing motion at thousands of kilometers per second. In young quasar-host galaxies, the environment is often rich in gas. This gas feeds star formation and may also feed the central black hole. Observations show dust, heavy elements, and fast-moving material in some distant systems, suggesting that stars have already formed and enriched the galaxy. Heavy elements are elements heavier than hydrogen and helium, made mainly through stellar processes. Their presence in early quasar environments indicates that galaxy growth is already advanced in certain regions. It remains uncertain how typical these systems are, because the brightest quasars are easier to find than quieter black holes. Selection matters strongly in quasar discovery. Telescopes detect the most luminous examples across great distances, while dimmer or obscured active black holes may remain hidden. This means the known distant quasar population may represent only the most visible part of a broader group. Dust can absorb ultraviolet and visible light, making some active centers appear weak or invisible in those wavelengths. Infrared and X-ray observations help reveal hidden activity. But even these methods have limits. The resulting picture is incomplete, yet it consistently shows that black hole growth begins early and can be highly efficient. The brightness of a quasar is also tied to a physical limit known as the Eddington limit. This is the point at which outward radiation pressure balances inward gravity for falling gas. If radiation becomes too strong, it can push material away and slow the feeding process. Some black holes may grow near this limit for long periods, while others may experience shorter episodes of more rapid or irregular feeding. The exact behavior depends on the shape of the gas flow, the amount of dust, magnetic fields, and the surrounding galaxy. Observations indicate that some early quasars require sustained growth, large starting seeds, or both. Around a quasar, gas does not remain still. Some material falls inward, some forms stars, and some is driven outward by radiation and winds. These outflows can travel through the host galaxy, carrying energy and heavy elements into wider regions. They may heat gas, compress it, or remove it from the central area. This process links the black hole to the future development of the galaxy. If gas is removed or kept hot, star formation may slow. If gas is compressed in certain regions, star formation may increase locally. The outcome depends on the structure of the galaxy and the strength of the activity. At great distances, the host galaxy around a quasar can be difficult to observe because the central source is so bright. Newer infrared observatories improve this view by detecting stretched light from old stars, dust, and gas. By reducing the glare of the central source, astronomers can begin to measure the size, mass, and shape of the host. Some distant quasar hosts appear disturbed, suggesting mergers or rapid inflow. Others show rotating gas, suggesting more organized growth. The evidence is still developing, and different systems may follow different paths. Quasars also reveal matter between galaxies. As their light travels across space, gas clouds along the path absorb specific wavelengths. These absorption features allow astronomers to study the distribution of hydrogen, heavier elements, and ionized gas across cosmic time. In this way, a quasar acts as a distant lamp shining through the universe. The black hole powers the lamp, while the intervening gas writes patterns into the light. These patterns help trace the large-scale environment around young galaxies and the changing state of intergalactic matter. Some quasars show changes in brightness over time. This variability suggests that the emitting regions are compact, because large regions cannot change rapidly as a whole. The timescale of variation helps estimate the size of the source. In distant quasars, observed time is stretched by cosmic expansion, so changes appear slower than they were at the source. Even with this effect, variability remains a useful sign of active accretion. It separates quasar light from the steadier glow of ordinary stellar populations. In this outer to inner path, quasars occupy the region where the black hole's presence becomes brighter, but still remains hidden by its own surroundings. The focus is not yet the close boundary of the black hole, but the active galaxy seen from afar. The quasar is a central engine embedded in a young system of gas, stars, dust, and motion. Its discoveries are unsettling because they show that intense black hole growth is already underway when the universe is still young. The darkness at the center is not visible, yet its surrounding light reaches across cosmic time, steady enough to be measured, distant enough to remain partly unknown, and powerful enough to shape the early galaxies that carry it. Within galaxies themselves, black holes are studied through the long relationship between central gravity and the surrounding supply of gas, stars, and dust. A galaxy is not a still island of light. It is a large system in motion, shaped by rotation, collisions, internal flows, and the slow exchange of matter between its central regions and its outer parts. In many large galaxies, the central region contains a supermassive black hole. This object may remain quiet for long intervals, yet its presence is linked to the structure and history of the galaxy around it. The connection is seen most clearly in patterns measured across many galaxies. The mass of a central black hole often relates to properties of the galaxy's central bulge, the dense gathering of stars near the middle. Galaxies with more massive bulges tend to host more massive central black holes. This relation does not mean that one object simply controls the other in a direct way. It shows that black hole growth and galaxy growth are connected through shared processes, especially the movement of gas into central regions and the effects of energy released during active phases. Gas is the key material in this layer of the subject. Cold gas can collapse into stars, feed the central black hole, or be stirred and heated until it no longer forms stars easily. A galaxy with abundant cold gas may glow with new star formation, while a galaxy with little cold gas may grow older and redder as its existing stars age. The black hole enters this balance when gas falls close enough to form an active galactic nucleus. The energy released near the center can then affect the surrounding gas, either by heating it, pushing it outward, or disturbing its motion. This exchange is called feedback. In plain terms, feedback is the return of energy from a growing black hole to the galaxy that feeds it. The word does not describe a single event. It includes radiation, winds, and jets that interact with gas over many scales. Radiation can heat nearby material. Winds can drive gas away from the center. Jets can pierce through surrounding gas and deposit energy farther out. The effect may be gentle and continuous in some galaxies, or stronger and more irregular in others. Observations indicate that feedback helps explain why some massive galaxies stop forming stars as rapidly as expected. Without some regulating process, large galaxies might keep cooling gas and forming stars at higher rates than are observed. Supernova explosions from massive stars provide one kind of regulation, especially in smaller galaxies. In more massive galaxies, active central black holes can provide another. Their energy can keep gas hot in the surrounding halo, where a halo is the extended region of gas and dark matter around the visible galaxy. If the halo gas remains hot, it does not fall inward efficiently. The central black hole therefore contributes indirectly to the galaxy's future by changing how much fuel becomes available. The relation is not one way. The galaxy also controls the black hole. A black hole cannot grow rapidly without a supply of gas. Bars, spiral arms, tidal forces, and galaxy mergers can all help move gas inward. A bar is an elongated structure of stars and gas that crosses the central region of some spiral galaxies. Its gravity can guide gas towards smaller orbits. Mergers can disturb gas on a larger scale, removing angular momentum, which is the tendency of rotating matter to keep moving around rather than falling inward. When gas loses enough angular momentum, it can drift closer to the center. Not every galaxy merger produces a bright active nucleus, and not every active nucleus requires a major merger. The evidence shows a range of pathways. Some black holes grow during dramatic interactions between galaxies. Others grow through quieter internal processes. The same galaxy may pass through many phases over its lifetime, with long calm intervals separated by shorter active episodes. The black hole's final mass records the sum of these episodes. While the galaxy's stars preserve a broader history of gas supply and star formation, the shape of a galaxy also matters. Spiral galaxies often contain disks rich in gas and dust, with star formation continuing across their arms. Elliptical galaxies tend to have older stars and less cold gas, though they may contain hot gas halos. Central black holes appear in both types, but their feeding conditions differ. In a gas-rich spiral, cold material may reach the center through slow internal flows. In a massive elliptical, the black hole may feed from hot gas cooling gradually, from stellar winds, or from gas brought in by smaller mergers. The activity level depends on how much material reaches the central region and how efficiently it loses energy. Observations at many wavelengths build this picture. Optical light shows stars and ionized gas. Infrared light reveals dust and older stellar populations hidden behind dust. Radio waves trace jets and cool gas in some conditions. X-rays show hot gas and energetic regions near active centers. No single wavelength provides the full story. A galaxy may look calm in visible light while showing radio jets or X-ray cavities. Another may show bright star formation that hides a weaker active nucleus. The combined evidence is needed to understand whether the central black hole is feeding, resting, or affecting gas at larger distances. The newest discoveries add weight to the idea that black holes and galaxies grow together from early times onward. Massive black holes appear in young galaxies, while nearby galaxies show long-term marks of central activity. The challenge is to connect these views into one continuous history. A single snapshot cannot reveal whether a black hole has recently slowed star formation, or whether it is only responding to gas already moving inward. Large surveys, simulations, and repeated observations help separate cause from coincidence. It remains uncertain in many individual cases how strongly a specific black hole changes its host galaxy, but the overall connection is well established. In this galactic region, the fear suggested by darkness becomes a quieter scientific seriousness. A black hole at a galaxy's center is not simply a hidden drain. It is part of an exchange system. Matter falls inward, energy returns outward, and the galaxy adjusts over long spans of time. Stars form, gas cools, gas heats again, and the central object grows by small and large increments. The discoveries are more profound than a single image of darkness because they show that black holes help shape the visible homes of stars. Their influence moves through gas, through heat, through motion, and through the long memory of galaxies, leaving patterns that remain visible long after the active phase fades. Within the Milky Way, the outer environment provides a quieter setting in which to understand the presence of a central black hole without the overwhelming brightness seen in distant quasars. The galaxy appears as a broad rotating disk of stars, gas, and dust, with spiral arms extending outward from a denser central region. From a position within this disk, the structure is not seen from above but experienced as a band of light across the sky, where countless distant stars blend into a continuous glow. The central black hole of the Milky Way lies deep within this band, far from the calm regions where most stars, including the Sun, reside. The outer parts of the Milky Way are relatively stable over human timescales. Stars move in long, predictable orbits around the galactic center, taking hundreds of millions of years to complete a single circuit. Gas clouds drift, compress, and form new stars in spiral arms. These processes occur far from the central region where gravitational forces become stronger and more complex. In this outer zone, the black hole does not dominate local motion. Its influence is present but subtle, embedded within the overall mass of the galaxy. The distance from the Sun to the galactic center is about 26,000 light-years. At this distance, the gravitational pull of the central black hole is far weaker than the combined effect of the galaxy's stars and dark matter. The Sun's motion is governed mainly by the total mass enclosed within its orbit, not by the black hole alone. This means that for most of the galaxy, the central black hole is not an immediate force, but part of a larger gravitational background. Its presence is known through careful measurement rather than direct effect on nearby stars. Observations of the Milky Way rely on multiple methods because dust within the galaxy absorbs visible light and obscures the central regions. Infrared light passes more easily through dust, allowing telescopes to peer closer to the center. Radio observations reveal cold gas and certain energetic processes. X-ray measurements show hot gas and compact sources. Together, these methods build a layered view of the galaxy, from the quiet outer disk to the crowded inner regions. In the outer disk, star formation occurs within molecular clouds, which are dense regions of cold gas. These clouds collapse under gravity, fragmenting into smaller regions that form stars. The process is influenced by turbulence, magnetic fields, and the pressure of surrounding gas. Black holes do not play a direct role in this local star formation. Their influence becomes more relevant closer to the center, where gas densities and gravitational forces increase. The outer disk therefore serves as a baseline, a region where the usual processes of stellar life proceed with little disturbance from the central black hole. The Milky Way also contains a halo, an extended region surrounding the disk. The halo includes old stars, globular clusters, and a large amount of dark matter. Some gas exists in this region as well, often at low density and high temperature. The halo interacts with the disk through slow flows of material. Gas may fall inward from the halo, replenishing the disk and supporting continued star formation. At the same time, energy from supernova explosions and other processes can push gas outward. The balance between inflow and outflow shapes the long-term evolution of the galaxy. The central black hole, known as Sagittarius A, remains distant from this outer environment, yet its existence is confirmed through precise measurements of the inner galaxy. Its mass is about 4 million times that of the Sun. This value is determined by tracking the motion of stars much closer to the center, where the black hole's gravity becomes dominant. In the outer regions, however, such direct influence is not observed. Instead, the black hole is one component of a much larger system, its presence felt only through the overall gravitational structure. The Milky Way is not isolated. It belongs to a small group of galaxies, including the Andromeda Galaxy and several smaller companions. These galaxies move within a shared gravitational field and may eventually merge over very long timescales. Such interactions can influence gas flow, star formation, and the growth of central black holes. In the outer regions, these effects are subtle, appearing as slow changes in motion or faint streams of stars pulled from smaller galaxies. The black hole at the center of the Milky Way does not directly shape these outer interactions, but it will become more relevant if large-scale mergers bring new material inward. Observations indicate that Sagittarius A is currently in a relatively quiet state. It emits some radiation, especially in radio and X-ray wavelengths, but far less than an active galactic nucleus in other galaxies. This suggests that the rate of gas falling into it is low at present. The reasons may include limited gas supply in the immediate vicinity or conditions that prevent efficient inward flow. The quiet state allows astronomers to study the surrounding region without the glare of intense activity, providing clearer measurements of stellar motion and gas distribution. In this outer galactic region, the understanding of black holes becomes more grounded. The central object is not a constant source of dramatic energy, but a stable part of a long-lived system. Its influence is real but distant, its effects woven into the overall structure rather than dominating daily motion within the disk. The Milky Way's outer environment shows that a galaxy can exist in relative balance, with star formation, gas flow, and stellar motion proceeding in steady patterns while a massive black hole rests quietly at the center. This calm setting forms a contrast with the brighter and more active systems seen at greater distances. It shows that black hole activity varies widely, and that periods of quiet may last for long spans of time. The outer Milky Way provides a reference point, a region where the black hole's presence is understood through careful measurement rather than direct interaction. From here, the path continues inward, toward regions where the central gravity becomes stronger, and where the motion of stars begins to trace the hidden mass more directly. Near the center of the Milky Way, the broad calm of the outer disk gives way to a denser and more crowded stellar environment. Stars gather more tightly, gas clouds move through stronger gravitational fields, and dust still hides much of the region from visible light. Infrared observations become essential because they pass more easily through the obscuring material. Through these observations, astronomers track individual stars moving around the compact radio source known as Sagittarius A, the object associated with the galaxy's central black hole. The most important evidence comes from stellar orbits. An orbit is the path one object follows under the gravity of another. In the central region, several stars move on sharply curved paths around an unseen mass. Their motion is fast, repeated, and measurable over years and decades. One star in particular, often called S2 in scientific literature, follows an elongated orbit that brings it very close to Sagittarius A before carrying it outward again. Its changing position and speed show that a large amount of mass must be concentrated in a very small volume. This evidence is strong because stars behave like test particles. They are bright enough to observe, and their motion responds to gravity. If the central mass were spread out across a large region, the orbits would have a different shape. Instead, the observed paths indicate a compact object with about 4 million times the mass of the Sun. The density required to place so much mass inside such a small space rules out ordinary clusters of stars, faint remnants, or gas clouds as stable explanations. The best explanation supported by observation is a supermassive black hole. The surrounding stars do not fall straight inward. They continue moving along their own paths, guided by a balance between their motion and the central gravity. Some orbits are stretched into long ellipses, while others appear less extreme. The closer a star comes to Sagittarius A, the more strongly its path curves and the faster it travels. At closest approach, some stars reach speeds of several thousand kilometers per second. These motions are still orderly, not chaotic in the simple sense. They follow gravity with high precision, allowing astronomers to test both the mass of the black hole and the predictions of general relativity. General relativity is the theory that describes gravity as the curvature of space-time. In the strong field near Sagittarius A, the orbits of stars show small effects beyond ordinary Newtonian gravity. One measured effect is the gradual shift of a star's orbit over time, where the closest point of approach changes slightly from one orbit to the next. Another effect appears in the light from a star as it climbs out of the gravitational field, losing energy and shifting toward longer wavelengths. These measurements do not require entering the black hole's immediate boundary. They come from stars outside it, moving through a region where gravity is strong enough to reveal subtle corrections. The central stellar environment is not empty between the stars. Gas and dust exist there as streams, clouds, and heated material. Some of it moves under the influence of winds from massive stars. Some may drift toward the central region, though only a small fraction appears to reach the black hole efficiently. The area is complex, with young massive stars, older stars, compact remnants, and magnetic fields all contributing to the motion of gas. Sagittarius A remains relatively dim compared with active black holes in other galaxies, suggesting that little matter is currently being swallowed. The faintness of Sagittarius A is itself an important discovery. Given its mass, it could be much brighter if gas were falling in at a high rate. Instead, it emits weak radiation in radio, infrared, and X-ray wavelengths. This means that most nearby gas either does not reach the black hole or falls inward in a way that converts only a small part of its energy into light. Models suggest that hot gas may swirl around the black hole in a thick, inefficient flow, with much of the material pushed away before it can cross inward. The exact details remain under study. The stars near the center also reveal the long history of the region. Some are old, belonging to the dense nuclear star cluster around the galactic center. Others are young and massive, which is surprising because the strong tides near the black hole can make ordinary star formation difficult. Tides are differences in gravitational pull across an object or cloud. Near a massive black hole, tides can stretch gas and prevent it from collapsing unless the gas is dense enough. Observations indicate that young stars do exist in this environment, so conditions must have allowed star formation there in the past. The process remains an active area of research. A star passing too close to a black hole can be torn apart by tides. Such an event is called a tidal disruption event. Around Sagittarius A, no clear recent event of this kind is observed in the present record, though the possibility exists over long timescales. The stars currently tracked near the center remain outside the dangerous region where complete disruption would occur. Their orbits provide a stable way to measure the black hole without being destroyed by it. The central region therefore becomes a natural laboratory, not because it is violent at every moment, but because gravity there is concentrated and observable. The precision of these observations depends on long-term patience. Astronomers compare images taken over many years, measuring tiny changes in stellar positions. They correct for the motion of Earth, the distortion caused by the atmosphere, and the crowded background of other stars. Adaptive optics, a method that adjusts telescope mirrors to reduce atmospheric blurring, helps sharpen the view. Space telescopes and large ground-based observatories contribute different strengths. Together, they turn a dusty and hidden region into a measurable gravitational map. In this inner galactic region, the black hole is no longer only an inferred feature of galaxy evolution. It becomes a measured mass at the focus of real stellar paths. The surrounding stars mark its position and reveal its strength. Their motion is calm in the sense that it follows physical law, yet extreme in speed and curvature compared with ordinary stellar motion farther out. The discoveries here are serious because they transform a hidden center into a precise object of study. Sagittarius A remains dark, compact, and quiet, while stars around it trace invisible gravity with steady motion, carrying the evidence in their path through the crowded heart of the Milky Way. Beyond the dense central cluster of the Milky Way, but still within the broader population of stars in galaxies, there exists a different class of black holes. These are stellar black holes, formed from the collapse of massive stars at the end of their lives. They are far smaller than the supermassive object at the galactic center, yet they are far more numerous. In this region of the subject, black holes are not anchored to the centers of galaxies but scattered among ordinary stellar populations, often hidden unless they interact with nearby matter. A stellar black hole begins when a star with sufficient mass exhausts its nuclear fuel. Nuclear fuel refers to the process by which stars fuse lighter elements into heavier ones, releasing energy that supports the star against gravitational collapse. When this process can no longer continue, the balance fails. The outer layers may be expelled in a supernova explosion, while the core collapses inward. If the remaining mass is large enough, no known force can stop the collapse. And a black hole forms. The result is a compact object with a mass typically several times that of the Sun, contained within a very small region. Most stellar black holes are difficult to detect directly. They emit no light unless matter falls toward them. Many exist alone, moving quietly through the galaxy, their presence inferred only through gravitational effects that are too small to measure at large distances. The most accessible examples are found in binary systems, where a black hole and a normal star orbit a shared center. In such systems, the black hole can draw material from its companion star. This material forms a hot, glowing flow before disappearing inward, producing X-rays that can be detected by space-based observatories. These systems are called X-ray binaries. The radiation arises because gas pulled from the companion star accelerates and heats as it spirals inward. Friction within the flow and compression of the gas convert gravitational energy into heat. The temperatures become high enough to emit X-rays, a form of high-energy light that passes through regions opaque to visible light. Observations of X-ray binaries allow astronomers to estimate the mass of the unseen companion. When the mass exceeds the known limit for neutron stars, which are another type of compact stellar remnant, the object is identified as a black hole. The motion of the visible star in a binary system provides a clear method of measurement. As the star orbits, its light shifts slightly toward shorter or longer wavelengths, depending on its motion toward or away from the observer. This effect, known as the Doppler shift, reveals the star's speed. By combining this information with the orbital period and the shape of the orbit, astronomers calculate the mass of the unseen companion. If the mass is too large to be a neutron star, the conclusion is that the companion is a black hole. Not all stellar black holes are found through bright X-ray emission. Some are discovered through their gravitational influence on stars without strong radiation. In these cases, precise measurements of stellar motion can reveal an unseen mass. Recent observations have identified a small number of candidates where a normal star orbits an invisible companion that does not emit strong X-rays. These quiet systems suggest that many more stellar black holes exist than are currently detected, because only a fraction are actively accreting matter at any given time. The distribution of stellar black holes reflects the life cycle of massive stars. Regions with recent star formation, such as spiral arms, may contain younger black holes formed from recent supernovae. Older regions may contain remnants of earlier generations of stars. Over time, black holes can drift from their birthplaces due to the motion of the galaxy and the effects of the explosion that formed them. Some may receive a slight push, known as a natal kick, during the supernova, altering their path through space. The exact distribution depends on these processes, which are still being studied. Observations also indicate that stellar black holes can vary in mass. Some have masses only a few times that of the Sun, while others reach several tens of solar masses. The upper range has been extended by detections of gravitational waves from merging black holes, suggesting that under certain conditions, stars can leave behind more massive remnants than previously expected. These conditions may involve low amounts of heavy elements, which affect how much mass a star loses during its lifetime. Less mass loss allows a heavier core to collapse into a black hole. The behavior of matter near stellar black holes can change over time. X-ray binaries often show cycles of activity, where the brightness increases and decreases. These changes reflect variations in the flow of gas from the companion star. At times, the flow becomes unstable, leading to bursts of radiation. At other times, the system becomes quiet. These cycles provide insight into how matter moves under strong gravity and how energy is released before material crosses the boundary of no return. In some systems, jets of material are launched away from the black hole along narrow directions. These jets can travel at high speeds and emit radio waves. The mechanism involves magnetic fields interacting with the rotating flow of gas. While the details are complex, the general picture shows that not all matter drawn toward a black hole is consumed. Some of it is redirected outward, carrying energy away from the system. This process appears in both stellar and supermassive black holes, suggesting a common physical principle across different scales. The presence of many stellar black holes within galaxies changes the understanding of how common these objects are. They are not rare singularities, but a natural outcome of stellar evolution. Each massive star that ends its life in collapse adds to this population. Most remain unseen, moving through the galaxy without noticeable effect on their surroundings. Only when they interact with other matter do they become visible as sources of radiation or as companions in binary systems. In this region, the discoveries show that black holes are not confined to galactic centers. They are distributed among stars, formed through ordinary processes that occur repeatedly over cosmic time. Their quiet abundance is more striking than any single dramatic event. It suggests that the galaxy contains many invisible points where gravity has reached its most compact form. These points do not announce themselves loudly. They wait, detectable only when chance brings matter close enough to reveal their presence through motion or light. Among the population of stellar black holes, some are not isolated and not paired with ordinary stars, but bound together with another black hole. These systems form when two massive stars evolve in the same region, each collapsing into a black hole and remaining gravitationally linked. Over long periods, their motion changes slowly, drawing them closer together. In this region of the subject, the focus turns to black hole binaries, where two compact objects orbit each other in a gradual inward spiral. At large separations, the two black holes circle a shared center of mass in a stable orbit. Each follows a curved path determined by the combined gravity of the pair. The system may be invisible if no matter surrounds it to produce light. Unlike X-ray binaries, there is often no companion star providing gas. The black holes move through space in near silence, their presence hidden except for the influence they exert on each other. Over time, however, a subtle process begins to remove energy from the system. This process involves gravitational waves. A gravitational wave is a ripple in space-time produced by the acceleration of massive objects. When two black holes orbit one another, their motion disturbs the fabric of space-time, sending out waves that travel outward at the speed of light. These waves carry energy away from the system. As energy is lost, the orbit shrinks. The black holes move slightly closer together, and their speed increases. This change is extremely gradual at first, taking millions or billions of years, depending on the initial separation. As the orbit tightens, the emission of gravitational waves grows stronger. The frequency and amplitude of the waves increase as the black holes draw nearer. Frequency refers to how often the waves pass a given point, while amplitude relates to their strength. In the final stages, the two black holes complete orbits in a fraction of a second. Their motion becomes rapid and intense, and the gravitational waves become strong enough to be detected by sensitive instruments on Earth. The detection of these waves marks a major advance in the study of black holes. Instruments such as LIGO and Virgo measure tiny changes in distance caused by passing gravitational waves. These changes are extremely small, far smaller than the width of a single atom. Yet they can be detected through precise interference of laser light. When a signal is observed, it carries a pattern that reflects the masses of the black holes, their distance, and the way they merge. By analyzing this pattern, scientists reconstruct the final moments of the binary system. The merger itself occurs when the two black holes come so close that their horizons combine. The horizon is the boundary beyond which no light can escape. As the black holes merge, they form a single, more massive black hole. The final object is not immediately stable. It undergoes a brief phase of adjustment, emitting gravitational waves in a pattern that fades over time. This phase is sometimes called ring down, referring to the way the signal decreases as the new black hole settles into a stable state. The masses of black holes involved in these mergers have provided new information about stellar evolution. Some detected black holes are more massive than those commonly found in X-ray binaries. This suggests that under certain conditions, stars can collapse into heavier remnants, possibly due to lower mass loss during their lifetimes. It also indicates that black hole binaries can form in different environments, including dense star clusters where interactions bring objects together over time. Not all black hole binaries form from pairs of stars that evolve together. In dense environments such as globular clusters, close encounters between stars and compact objects can lead to the formation of new pairs. A black hole may capture another black hole through gravitational interaction, forming a binary that did not begin as a stellar pair. These dynamical formations add complexity to the population of merging systems and affect the distribution of masses and orbital properties. The detection of gravitational waves has also revealed that black hole mergers are not rare on cosmic timescales. While individual events are brief, The number of detections has grown steadily as instruments improve. Each detection provides a new data point, helping to map the population of black holes across the universe. The signals come from different distances, corresponding to different times in cosmic history. This allows a partial reconstruction of how black hole mergers have occurred over billions of years. In some cases, the merged black hole may receive a recoil, a slight motion caused by asymmetry in the emitted gravitational waves. If the waves carry more momentum in one direction, the final object moves in the opposite direction. This recoil can shift the black hole from its original position. In extreme cases, it may even be displaced from the center of its host system. Observations of such events remain challenging, but the theory is supported by detailed models and some indirect evidence. Black hole binaries show that these objects do not only act on surrounding matter, they also interact directly with each other through gravity. The process is quiet in the sense that it produces no light, yet it reshapes space-time itself. The waves they emit travel across the universe, carrying information about events that would otherwise remain hidden. This opens a new method of observation, where the universe is studied not only through light but through the motion of space-time. In this region, the discoveries deepen the understanding of black holes by showing their interactions beyond simple accretion. They can pair, orbit, and merge, creating signals that pass through space without obstruction. The process is governed by precise physical laws, unfolding over immense periods before ending in a brief, powerful event. The black holes themselves remain dark, but their motion leaves a measurable trace, extending the reach of observation into a domain where light alone cannot reveal what is taking place. Around an active black hole, far outside the final boundary, matter begins its slow and uneven approach through a broad region of gas and dust. This outer accretion environment is not a simple stream falling straight inward. It is a complex surrounding structure shaped by rotation, gravity, pressure, radiation, and magnetic fields. Accretion means the gathering of matter onto a central object in black hole systems. Accretion begins when nearby material loses enough energy and angular momentum to move closer to the center, but it still remains outside the black hole and outside the most extreme inner region. The material may come from many sources. In a galaxy center, gas can drift inward from larger galactic scales through bars, spiral structures, collisions, or slow cooling. In a stellar system, gas may come from a companion star. In both cases, matter rarely falls directly downward. It usually carries rotation, so it spreads into a flattened or thickened flow around the black hole. The gas circles the central object while gradually moving inward. This motion creates an accretion disk or, in some cases, a broader accretion flow. The exact shape depends on temperature, density, magnetic fields, and the rate at which matter is supplied. In the outer accretion region, temperatures are lower than they are close to the black hole, but they can still be high compared with ordinary interstellar gas. Dust may survive in the farther parts, absorbing shorter wavelength light and re-emitting energy as infrared radiation. Gas clouds may orbit in uneven clumps, sometimes forming a thick ring or torus around the active center. A torus is a donut-shaped distribution of matter. It can hide the bright inner regions from some viewing angles, explaining why active black holes appear different depending on the line of sight. When the view passes through dense dust, the center looks obscured. When the view has a clearer path, the central light is easier to detect. This outer material plays a major role in how active black holes are classified. Some active galactic nuclei show broad emission lines, produced by gas moving rapidly near the center. Others show only narrow lines, because the faster inner gas is hidden behind dust and gas. The difference may not mean the central engine is fundamentally different. It may mean that the same kind of system is viewed from another angle, or surrounded by different amounts of obscuring matter. This model is useful, though not complete, because real systems vary in structure, gas supply, and activity level. The outer accretion region is also where gravity begins to organize chaotic matter into a more directed flow. Gas clouds collide, compress, and exchange energy. When gas particles interact, some lose angular momentum and move inward, while other material may gain angular momentum and move outward. This exchange allows accretion to continue. Without a way to shed angular momentum, matter would remain in orbit rather than approaching the black hole. Turbulence and magnetic fields are believed to help drive this transport, though the details remain difficult to observe directly. At these distances, the black hole's gravity is important, but not alone. The mass of surrounding stars, gas, and dark matter may still contribute to the overall motion, especially in galactic centers. The accreting material is influenced by the broader environment. In a gas-rich galaxy, steady supply may feed the center for a long time. In a gas-poor galaxy, the black hole may remain faint. In a binary star system, the companion star's gravity shapes the flow, sometimes forming a stream that strikes the outer edge of the disk. The black hole's feeding is therefore not isolated from its setting. It depends on how matter arrives from outside. Radiation from the inner regions can travel outward and reshape the outer accretion zone. Light heats dust and gas, changing their temperature and pressure. Strong radiation can push on dust grains, driving winds away from the center. These winds may carry material that would otherwise continue inward. In this way, accretion can limit itself. Matter feeds the active center, the center releases energy, and that energy can slow or redirect the supply. This balance helps explain why black holes do not simply consume all nearby gas as quickly as possible. In some active galaxies, observations show broad outflows moving at high speeds. These outflows may begin closer in but become visible as they pass through the outer accretion environment. They carry ionized gas, dust, and heavy elements into the surrounding galaxy. Ionized gas is gas whose atoms have lost electrons. The outflows can appear in absorption lines, where gas along the line of sight removes specific wavelengths from the central light. They can also appear in emission, where energized gas glows. The presence of these winds shows that the outer region is not only a feeding zone but also a place where returning energy shapes the nearby environment. The outer accretion region changes over time. It may brighten when more gas arrives, dim when the supply weakens, or shift between states as the disk structure changes. In stellar mass systems, such changes can happen over days, weeks, or months. In supermassive black holes, similar processes unfold over much longer times because the system is larger. Yet the same basic principles apply across scale. Matter rotates, heats, exchanges energy, and moves inward only when physical processes allow it to lose angular momentum. New observations continue to refine this picture. Infrared measurements reveal dust heated by hidden active centers. X-ray observations show absorbing gas and high-energy emission. Radio data trace outflows and compact cores. Time domain surveys, which repeatedly observe the same regions of sky, reveal changes in brightness that indicate shifting accretion. These measurements show that black hole feeding is not a steady drain but a changing process, shaped by both supply and resistance. In this outer accretion region, the black hole becomes more immediate, yet it is still not directly reached. The surrounding matter remains outside the deepest gravity. Moving through a wide zone where dust may survive, gas may cool or heat, and radiation may escape or be absorbed. The discoveries here are unsettling because they show how ordinary material begins to enter an extreme physical system. Gas that once belonged to stars, clouds, or galaxies becomes organized into a flow around darkness. It does not vanish at once. It circles, collides, glows, thickens, thins, and only slowly gives up the motion that keeps it away from the center. Deeper within the accretion flow, the structure becomes more ordered, more energetic, and more tightly bound to the gravity of the black hole. The inner accretion disk forms where matter has already lost a significant amount of angular momentum and now orbits at high speed in a flattened, rotating layer. In this region, distances are much smaller, temperatures are much higher, and motion becomes more extreme. The disk glows not because the black hole emits light, but because the orbiting material releases energy as it spirals inward. The gas in the inner disk moves along nearly circular paths, each layer rotating at a different speed. Material closer to the black hole travels faster than material farther out. This difference in speed creates shear, a condition where adjacent layers slide past one another. Shear leads to friction-like effects within the gas, even though the medium is thin and not a solid. This internal stress converts orbital energy into heat. As a result, the temperature rises significantly, reaching millions of degrees Celsius in some regions, especially around stellar mass black holes. In supermassive systems, the temperatures may be lower at the same relative distance, but still high enough to emit strong radiation. The inner disk radiates across a wide range of wavelengths. In stellar mass systems, much of the emission appears in X-rays. In supermassive systems, the peak may lie in ultraviolet or optical wavelengths, depending on the mass and the rate of accretion. This radiation provides a direct view of the physical conditions close to the black hole, the spectrum, meaning the distribution of a light across different wavelengths, carries information about temperature, density, and motion within the disk. By studying these patterns, astronomers infer how matter behaves under intense gravity. The structure of the inner disk is not perfectly smooth. It is influenced by turbulence, magnetic fields, and instabilities that arise from the motion of ionized gas. Ionized gas, also called plasma, consists of charged particles that interact strongly with magnetic fields. One key process believed to operate in accretion disks is the magnetorotational instability. This mechanism helps transfer angular momentum outward, allowing matter to drift inward. Without such processes, the disk would remain stable in orbit and accretion would be inefficient. The instability creates a tangled pattern of motion that redistributes energy and momentum through the disk. As matter moves inward, it reaches regions where the gravitational potential becomes extremely deep. The energy released per unit mass increases, making the inner disk far more luminous than the outer regions. The radiation pressure, which is the force exerted by light on matter, can become significant. In some cases, it may partially counteract gravity, especially when the accretion rate is high. This balance influences the thickness of the disk. At lower rates, the disk remains relatively thin. At higher rates, it can puff up into a thicker structure, altering how light escapes and how matter flows. Close to the black hole, relativistic effects become important. Relativity describes how space and time behave under strong gravity and high speed. One effect is gravitational redshift, where light loses energy as it climbs out of the deep gravitational field, shifting toward longer wavelengths. Another effect is time dilation, where processes near the black hole appear slower when observed from far away. The motion of the disk also leads to Doppler shifting, where light from material moving toward the observer is shifted to shorter wavelengths, while light from material moving away is shifted to longer wavelengths. The combination of these effects produces characteristic shapes in the observed spectrum. The inner edge of the accretion disk is defined by a critical orbit known as the innermost stable circular orbit. This is the smallest radius at which matter can maintain a stable circular path. Inside this boundary, orbits become unstable and matter begins to plunge inward more directly. The location of this boundary depends on the mass and spin of the black hole. Spin refers to the rotation of the black hole itself, which affects the structure of space-time around it. A rapidly spinning black hole allows stable orbits closer in than a non-rotating one. Measuring the position of the inner edge can therefore provide clues about the black hole's spin. Observations of the inner disk often show rapid variability. Brightness can change on short timescales, reflecting changes in the flow of matter or instabilities within the disk. In stellar mass systems, these changes may occur over fractions of a second. In supermassive systems, they unfold over longer intervals, from hours to days or more. The variability provides insight into the size of the emitting region, because faster changes imply a smaller region. It also reveals that the accretion process is not perfectly steady, but fluctuates as conditions evolve. In some cases, the inner disk produces characteristic features known as quasi-periodic oscillations. These are variations in brightness that occur at nearly regular intervals. They are thought to arise from patterns of motion within the disk, possibly linked to orbital frequencies near the innermost stable orbit, or to waves propagating through the plasma. The exact origin remains uncertain, but the phenomenon provides another tool for probing conditions close to the black hole. The energy released in the inner disk does not remain confined. Radiation travels outward, interacting with outer regions of the accretion flow and the surrounding environment. Some energy may also be carried by particles moving along magnetic field lines, contributing to the formation of jets that extend far beyond the disk. The inner disk is therefore both a source and a mediator, converting gravitational energy into radiation and influencing regions much farther away. In this region, matter approaches the limits of stable motion under gravity. The disk is luminous, dynamic, and shaped by processes that operate under extreme conditions. The black hole itself remains unseen, but its presence defines the structure and behavior of everything nearby. The discoveries here are significant because they reveal how ordinary matter is transformed into intense radiation through motion and interaction, without crossing the final boundary. The inner accretion disk stands as the last bright region before the transition into the darker domain, where escape becomes impossible. Threaded through the inner accretion disk and extending far beyond it, magnetic fields guide some of the most striking structures associated with black holes. These fields are not solid lines, but regions where forces act on charged particles within the plasma. In the hot, ionized gas of the inner disk, particles respond strongly to magnetic influence. The motion of the disk, combined with turbulence and rotation, stretches and twists these magnetic fields into complex shapes. Under certain conditions, this structure becomes organized enough to channel energy and matter outward in narrow, directed flows known as jets. A jet is a stream of particles and energy that moves away from the vicinity of the black hole along a preferred direction, often aligned with the rotation axis of the system. While much of the surrounding matter spirals inward, a small portion is redirected and accelerated outward. This does not contradict the nature of the black hole, because the material in jets originates from regions outside the event horizon. It is launched before crossing the final boundary. The energy that powers the jet is drawn from the motion of the accreting gas and, in some models, from the rotation of the black hole itself. The process that forms jets involves the interaction between rotating plasma and magnetic fields. As the disk spins, it can wind up magnetic field lines, storing energy in their twisted configuration. When the field becomes sufficiently ordered and strong, it can act like a guide for particles, directing them away from the disk. The particles follow these field lines and gain speed, sometimes approaching a significant fraction of the speed of light. The exact mechanism is complex and remains an area of active research, but the general picture is supported by observations and theoretical models. Jets can extend far beyond the region where they begin. In stellar mass systems, they may stretch across distances comparable to the size of the surrounding stellar environment. In supermassive systems, they can reach far outside the host galaxy, interacting with intergalactic space. As the jet travels, it carries energy and momentum into the surrounding medium. This interaction can heat gas, compress it, or create large-scale structures such as radiolobes, which are extended regions of the emission produced when jet material slows and spreads out. The appearance of jets depends on the wavelength of observation. In radio wavelengths, they often appear as long, narrow structures with bright knots where the flow interacts with surrounding matter or where shocks form. A shock is a sudden change in pressure and density that can accelerate particles and produce radiation. In X-rays, jets may reveal high-energy regions closer to their origin or sites of strong interaction. Optical observations can sometimes detect emission from fast-moving particles, though dust and gas may obscure parts of the structure. Not all black holes produce strong jets. The presence and strength of a jet appear to depend on several factors, including the rate of accretion, the structure of the magnetic field, and the spin of the black hole. A rapidly rotating black hole may contribute energy to the jet through a process that extracts rotational energy from the curved space-time around it. This idea is supported by models, though direct confirmation is difficult. Observations indicate that some systems with similar mass and accretion rates show different jet behavior, suggesting that multiple conditions must align for a powerful jet to form. The base of a jet near the inner disk is a region of intense activity. Here, magnetic fields are strongest and the plasma is hottest. The flow transitions from a rotating disk to a collimated stream, meaning it becomes more tightly aligned along a single direction. Collimation is essential for maintaining the jet over long distances. Without it, the outflow would spread out and lose its structure. Magnetic fields appear to play a central role in this collimation, guiding the particles and maintaining the narrow shape. As jets move outward, they interact with the environment in different ways depending on the density of the surrounding medium. In a dense environment, the jet may slow more quickly, depositing energy close to the source. In a less dense environment, it can travel farther before dispersing. These interactions can create cavities, shocks, and large-scale patterns in the surrounding gas. In galaxy clusters, jets from central black holes are observed to inflate bubbles in the hot intracluster medium, affecting the temperature and motion of gas across large regions. Jets also produce variability in the observed light from black hole systems. Changes in the flow of matter, the configuration of magnetic fields, or the interaction with surrounding material can alter the brightness and structure of the jet. These changes may occur on timescales that reflect the size of the system. In smaller systems, variations can happen rapidly. In larger systems, the changes are slower but can still be observed over years or decades. The particles within jets can include electrons and other charged particles accelerated to high energies. These particles emit radiation through processes such as synchrotron emission, where charged particles spiral around magnetic field lines and release energy. This radiation spans a wide range of wavelengths, from radio waves to X-rays, depending on the energy of the particles and the strength of the magnetic field. By studying this emission, astronomers infer the conditions within the jet and the processes that accelerate particles. Jets demonstrate that the region around a black hole is not only a place of inward motion, it is also a place where energy is redirected outward in a structured and sustained way. The balance between accretion and outflow shapes the environment on multiple scales. While most matter moves inward, a fraction escapes, carrying energy far from the center. This outward movement can influence star formation, gas distribution, and the long-term evolution of the host system. In this region, the discoveries show that black holes are not simply endpoints of motion. They are part of a dynamic system where energy flows both inward and outward. Magnetic fields, though invisible, organize this flow and give rise to structures that extend far beyond the immediate vicinity of the black hole. The jets appear calm in their steady direction, yet they carry immense energy over vast distances. Their presence reveals that even near one of the most extreme boundaries in nature, ordered patterns can emerge, guided by physical laws that operate across scales. Closer to the black hole, light itself begins to define the visible structure. The region is no longer described mainly by dust, broad gas flows, or long jets, but by the paths that photons follow through strongly curved space-time. A photon is a particle of light. Near a black hole, photons can travel along paths that bend sharply, loop partly around the center, or escape only after passing through a narrow range of possible directions. This is the region where the black hole becomes visible not through its own light, but through the dark shape it creates against the glow of nearby matter. The most familiar image from this region is the black hole shadow. The shadow is not the event horizon itself. It is a dark area on the sky caused by light paths that fall into the black hole rather than reaching the observer. Around this dark region, light from hot gas becomes distorted into a bright, uneven ring. The ring appears because photons from the surrounding emission are bent by gravity. Some travel from the far side of the black hole and curve around it before escaping outward. The result is a compact image where the central darkness is larger than the actual horizon would appear, because the bending of light enlarges the apparent boundary. The photon ring is a related feature, formed by light that passes very close to unstable circular paths around the black hole. A circular photon path is an orbit where light moves around the black hole, instead of immediately escaping or falling inward. These paths are unstable, meaning that a small change sends the photon either outward or inward. In practice, photons do not remain there for long. Some complete part of an orbit before escaping, carrying an image of the extreme curvature near the black hole. The photon ring is expected to be thin and difficult to isolate, but it forms an important part of the theoretical structure of black hole images. The image of a black hole depends on the glowing matter around it. Without nearby emission, the shadow would not stand out. In the observed images of supermassive black holes, the bright ring comes from hot plasma in the inner accretion flow. This plasma emits radio waves that can be detected by telescopes linked across Earth. By combining many observatories, scientists create a virtual telescope with a size comparable to the planet. This method is called very long baseline interferometry. It allows extremely fine angular resolution, meaning the ability to distinguish small details on the sky. The first images of black hole shadows show broad rings rather than perfect sharp outlines. This is expected because the emitting gas is turbulent, magnetized, and moving at high speed. One side of the ring often appears brighter than the other because gas moving toward the observer is boosted by relativistic effects. Light from approaching material appears brighter and shifted compared with light from receding material. The exact brightness pattern changes with time as the plasma moves. The shadow itself remains tied to the geometry of the black hole, while the surrounding glow reflects the changing conditions of the accretion flow. For the black hole at the center of the galaxy Messier 87, the observed ring corresponds to a supermassive object with billions of times the mass of the Sun. For Sagittarius A at the center of the Milky Way, the ring corresponds to a much smaller supermassive black hole, with about 4 million solar masses. The two images are similar in basic shape because black holes follow the same relativistic rules, but they differ in scale and variability. Sagittarius A changes more quickly because its smaller mass means the surrounding gas completes orbits in shorter times. This makes imaging more difficult, as the source changes while observations are being collected. The shadow provides a test of general relativity in a strong gravitational field. The size and shape of the shadow depend on the black hole's mass, spin, and the viewing angle. If observations showed a very different shape from predictions, it would suggest that the theory needs revision, or that the object is not a black hole as understood by current physics. So far, observed shadows are broadly consistent with black hole models based on general relativity. The measurements still contain uncertainties because the image depends on the structure of the surrounding plasma, not on geometry alone. The region also reveals how gravity affects the direction of time and light. Photons escaping from near the black hole lose energy, becoming redder as they climb outward. Light paths from different regions can arrive at the observer at different times, even if they were emitted together. Some paths curve around the black hole, taking longer routes. This means the image is not a simple surface picture, but a layered record of light emitted from different locations and moments. The ring blends these paths into one visible structure. The darkness at the center is not empty space in the ordinary sense. It is the absence of escaping light from directions that lead into the black hole. The shadow marks a region where the paths available to photons are captured. The surrounding brightness is shaped by the last possible escapes, where light still finds a route outward after being strongly deflected. This contrast gives the black hole its visual form. It is not a solid edge. Yet it behaves like a boundary in the image because light either reaches the observer or does not. New observations aim to sharpen this region further. More telescopes, higher frequencies, and longer observing campaigns improve the ability to separate the photon ring from the broader emission. Polarization measurements also add information. Polarization describes the orientation of light's electric field. In black hole images, polarization traces magnetic field structure in the emitting plasma. This helps connect the shadow region to the inner accretion flow and the base of any jet. The interpretation remains complex, but it provides a way to study invisible magnetic order near the black hole. In this near-horizon region, discoveries become more direct while still remaining observationally delicate. The black hole is not seen as an object with a surface. It is seen as a dark imprint surrounded by light that has been bent, delayed, brightened, and stretched by gravity. The ring is not a simple glow, but a map of curved paths. The shadow is not a hole in an image, but a record of photons that cannot escape. This region shows black holes as nature defines them most clearly from the outside, through the behavior of light approaching the limits of return. At a still deeper level, the region of interest is no longer defined by the appearance of light alone, but by the boundary that separates all possible outward paths from those that lead only inward. This boundary is known as the event horizon. It is not a surface in the ordinary sense, not made of material, not visible by direct emission. It is a limit in space-time, defined by the paths that light and matter can take. Outside this boundary, a photon may still find a direction that leads away from the black hole. At the boundary, all outward directions are balanced on the edge of capture. Inside it, no path leads back outward. The event horizon can be described as the distance from the black hole at which the escape speed equals the speed of light. Escape speed is the velocity needed for an object to move away from a gravitational field without falling back. For ordinary objects, this speed increases as gravity becomes stronger. At the horizon, the required speed reaches the maximum possible in nature. Since nothing can exceed the speed of light, nothing can escape once it crosses inward. This description is a simplified way of expressing a deeper idea from general relativity, where gravity is understood as the curvature of space-time rather than a force in the classical sense. From the outside, the horizon does not appear as a solid barrier. Matter approaching it does not encounter resistance or a physical wall. Instead, the behavior of time and light changes in a way that becomes more extreme as the boundary is approached. To a distant observer, processes near the horizon appear to slow down. A clock moving toward the horizon appears to tick more slowly compared with a clock far away. Light emitted from near the boundary becomes increasingly red-shifted, losing energy and shifting toward longer wavelengths. As a result, an infalling object appears to fade and slow, never quite reaching the horizon in the observer's view. This effect is known as gravitational time dilation. It does not mean that the object itself experiences a halt. In its own frame of reference, the object continues inward without noticing a sudden change at the boundary, assuming it is large enough that tidal forces are not extreme at that distance. The difference arises because observers at different positions measure time differently under strong gravity. The horizon marks a limit where these differences become so large that communication outward is no longer possible. The size of the event horizon depends on the mass of the black hole. For a non-rotating black hole, the radius is directly proportional to its mass. A stellar black hole has a horizon only a few kilometers across. A supermassive black hole has a horizon that can extend over millions of kilometers. Rotation adds complexity. A rotating black hole, described by the Kerr solution in general relativity, has a horizon whose shape and properties differ from the non-rotating case. The rotation also introduces a region outside the horizon called the ergosphere, where space-time itself is dragged around the black hole. In this region, objects cannot remain stationary relative to distant space. The event horizon remains the defining boundary regardless of rotation. It is the limit beyond which all paths lead inward. No signal, no particle, and no light can cross it outward. This property gives the black hole its name. The region inside cannot communicate with the outside universe. Observations can approach this boundary as closely as possible, but they cannot reveal events beyond it directly. All knowledge of the horizon comes from its effects on nearby matter and radiation. Near the horizon, the accretion flow transitions from orbiting motion to inward plunge. Outside the innermost stable orbit, matter can circle the black hole in relatively stable paths. As it moves inward past this orbit, the paths become unstable, and matter begins to fall more directly. The change is not a sudden drop, but a shift in the nature of motion. The gas accelerates inward, and its density and temperature can change rapidly. Radiation emitted from this region carries information about the final stages of the inflow before crossing the boundary. The behavior of light near the horizon is shaped by strong curvature. photons emitted close to the boundary may be bent sharply, with only a narrow range of directions allowing escape. Many photons that would move outward in a weaker field are instead turned back. This contributes to the appearance of the shadow described earlier. The horizon itself remains unseen, but the pattern of light around it reveals its presence. The closer to the boundary the light is emitted, the more extreme the bending and redshift become. Theoretical work suggests that the horizon may also be associated with subtle quantum effects. One such effect is Hawking radiation, a prediction that black holes can emit a very weak form of radiation due to quantum processes near the horizon. This radiation is extremely faint for astrophysical black holes and has not been directly observed. It implies that black holes may lose mass over very long timescales. For large black holes, this process is negligible compared with accretion. The concept remains important for understanding the connection between gravity and quantum physics, though it does not affect most observational features discussed here. The event horizon represents a limit of knowledge in observational astronomy. Measurements can approach it from the outside, using light, motion, and radiation to infer conditions near it. The exact behavior at the boundary is described by well-tested physical theory. Yet direct observation of crossing events is not possible from the outside. This makes the horizon both a defined and an inaccessible region. It is precisely located in theory, yet it marks the end of what can be directly observed. In this region, the discoveries are quiet but final in their implication. The event horizon is not dramatic in appearance, yet it defines the nature of a black hole more clearly than any other feature. It is the point at which the outward path ends. Matter and light approach it through the structures described earlier, glowing, moving, and interacting. At the boundary, those processes continue inward, but no signal returns. The outer universe records only the approach, the slowing, and the fading. The boundary itself remains as a limit, steady and absolute, separating what can be known from what lies beyond. Beyond the event horizon, the subject reaches the deepest limit of current observation. The interior of a black hole cannot be seen from outside, because no light or signal can return once it has crossed the boundary. Scientific understanding of this region therefore comes from theory rather than direct measurement. General relativity describes how space-time behaves inside the horizon, and its equations indicate that all inward paths lead toward a central region where curvature grows without limit. This predicted region is called a singularity. A singularity is not known as a physical object with ordinary structure. It is a sign that the theory has reached a point where its description becomes incomplete. Inside the horizon, the usual language of direction becomes difficult. In ordinary space, a person can choose to move left, right, forward, backward, inward, or outward, near and inside a black hole. Space-time is shaped so strongly that all future directed paths lead deeper inward. This does not mean that matter is pulled by a force in the usual sense. It means that the geometry of space-time itself is arranged so that the future points towards smaller radius, once inside. Moving toward the center is as unavoidable as moving forward in time. For a non-rotating black hole, the mathematical description is relatively simple. The horizon surrounds a central singularity, and anything crossing inward reaches that central limit in a finite amount of its own time. For a rotating black hole, the structure is more complex. Rotation changes the shape of space-time and produces additional theoretical features inside the horizon. These include inner horizons and a ring-like singularity in the exact mathematical solution. It remains uncertain how these idealized features behave in real astrophysical black holes, wherein falling matter, radiation, and disturbances are always present. The central issue is that general relativity does not include quantum mechanics in a complete way. Quantum mechanics describes matter and energy at very small scales. General relativity describes gravity and space-time at large and strong scales. Both theories are extremely successful in their own domains, but inside a black hole, especially near the predicted singularity, both are expected to matter. A complete theory of quantum gravity is needed to describe this region fully. Such a theory remains unfinished. For this reason, statements about the deepest interior must remain careful. Matter entering a black hole does not remain observable as ordinary material from the outside. Its mass, electric charge, and spin contribute to the black hole's overall properties. These are the quantities that can influence the exterior gravitational and electromagnetic fields. Other details, such as the precise arrangement of atoms or the history of the object, are not accessible from outside. This leads to the black hole information problem, a major question in theoretical physics. The problem concerns how information about matter that falls into a black hole is preserved, transformed, or hidden, especially if black holes slowly emit Hawking radiation over immense timescales. Hawking radiation suggests that black holes are not completely permanent. Through quantum effects near the horizon, they may lose energy very slowly. For black holes formed from stars or found in galaxy centers, this radiation is far too weak to observe with present instruments and far too small to affect their current growth. Yet in theory, over spans vastly longer than the present age of the universe, a black hole could lose mass and shrink. The question then becomes what happens to the information contained in everything that entered it. Modern theoretical work generally expects information not to be destroyed, but the exact mechanism remains debated. The interior also raises questions about tidal forces. Tidal forces are differences in gravity across an object. Near a small stellar black hole, these differences can become extreme near the horizon, stretching matter strongly along one direction and compressing it in another. Near a supermassive black hole, the horizon is much larger, and tidal forces at the boundary can be weaker. An object crossing such a horizon might not experience a sudden local event at that exact boundary. Though deeper inward, the tidal forces would grow. This distinction shows that the horizon and the singularity are different concepts. The horizon is the boundary of no return. The singularity is the predicted limit where current theory fails. No observation can follow matter through the horizon. From outside, telescopes can study the final light emitted before crossing, the surrounding disk, the shadow, the jets, and the gravitational waves from mergers. These signals all come from outside or from the changing horizon during a merger. They do not reveal the interior directly. Even gravitational waves from merging black holes describe the exterior space-time settling into a final form. They confirm the behavior of horizons and strong gravity, but they do not provide a direct image of what lies within. The phrase terrifying, when treated scientifically, does not mean immediate danger in this inner region. It means that the known laws point toward a domain where ordinary intuition no longer applies and where tested theories become incomplete. A black hole interior is not a place that can be mapped by light, sampled by instruments, or compared with ordinary matter. It is a region hidden by causal structure, where the boundary prevents information from returning. The seriousness lies in this separation between strong theoretical prediction and permanent observational silence. Still, black holes are not outside nature. They are predicted by general relativity, detected through many independent observations, and connected to the life cycles of stars and galaxies. Their interiors mark the edge of current understanding, not the end of reason. The equations guide the path inward until they indicate their own limitation. At that point, science does not fill the darkness with certainty. It names what is known, identifies what is uncertain, and waits for deeper theory. In this final inner region, the path reaches the place where direct knowledge stops. Outside the horizon, black holes reveal themselves through light, motion, heat, magnetic fields, and waves in space-time. Inside, those signals no longer return. The deepest interior remains described by mathematics and constrained by the behavior of the boundary around it. The discoveries are more profound than imagined because they show that the universe contains regions where gravity not only bends paths, but closes them. The black hole becomes a quiet limit, holding matter, energy, and unanswered questions behind a boundary that the outside universe can approach, measure, and never cross in return. The wider view settles into stillness. Across space, black holes remain as quiet limits within the order of the universe. Some rest at the centers of galaxies. Some move unseen among stars. Some merge and send faint waves through space-time. Some gather gas into bright rings before the light fades from view. Each one belongs to the same physical story, shaped by gravity, motion, heat, and time. The discoveries do not place them outside nature, they place them deeper within it. They show that darkness can be measured by the motion of stars, by the bending of light, by the glow of falling gas, and by ripples crossing the universe. They show that absence can leave structure, and that a boundary no light can cross can still shape what is visible around it. The event horizon remains steady in thought, a quiet edge where outward paths end. Beyond it, direct signals do not return. The inner region stays hidden, not by distance alone, but by the structure of space-time itself. Current physics reaches close, describes much, and then becomes careful. What is known remains firm. What is uncertain remains named without being forced into certainty. In the calm after the long inward path, the black hole is neither a sudden spectacle nor a simple emptiness. It is a region where gravity gathers the past of matter and holds it behind a boundary. Around it, the universe continues moving. Stars orbit. Gas cools and heats. Galaxies turn slowly through time. Light travels outward from the edge of darkness, carrying the last visible signs into space.